So we continue with the series on important clarification, or what we call important clarification series. And we are working on support vector machine due to its unique capability in several unique situations that we might find ourselves wherever we model using machine learning or in data science activities. Foremost of these unique capabilities of support vector machine include, among others, the ability to perform or to achieve impressive performance in the face of high dimensional data. That is where the number of features are so enormous or so huge that others might not be able to perform. Where other machine learning algorithms might not be able to perform, support vector machine have the capability of achieving very rare and unique outcome. And we've explained to ourselves that one of the secret behind this unique performance in the face of huge dimensionality or huge feature availability is that it makes you concentrate more on the support vector as the representative samples to be used after successfully training the model and then identify those unique support vectors. And then the second situation, among others, where support vector machine has often produced impressive performance compared to others, is when you have very few data samples. Because there are situations whereby the samples are just so few, and you don't have that freedom or luxury of increasing the sample yourself. This is the only data set the client can lay their hand on. So we've identified these very two unique cases, and there are other advantages and unique characteristics of support vector machine. So we started a couple of weeks ago with the unique advantages, characteristics of support vector machines. We have described them. We've also looked into the historical background and application of support vector machine in our earlier videos. Last time we were able to also took us through the idea of the one we call linear support vector machine. So that is when you have a very simple data, that the data is linearly separable. So it becomes very easier to use. However, in real life, in many situations we might face, the data set might not fall into those that are linearly separable. So in this case, support vector machine has a very unique capability, which we call the kernel trick. So it's able to make use of this kernel trick to solve this kind of problem, especially in the face of what we call non-linear problems. Therefore, so today we are going to focus on the nonlinear aspect of support vector machine and how the problem are often solved. Yeah. So this is what we are considering today. So when we talk of nonlinear SVMs, that is, we're talking of SVM that has the capability to solve cases where data set is too hard. It's not linearly separable. See, like this case is very simple case. It is linearly separable. You have a class here, you have another class here. So you can easily draw the separating hyperplane, and then you can then use the other procedure we have described to get the problem solved. However, in real life, you get the data set, when you try to draw a single line, it's not possible. Because you can see there's a class here, the part of this class is also here. So there's no way you can separate it by any hyperplane. You cannot draw it here, you cannot draw it here. Because it must be separated by one unique hyperplane. So in that case, we have to find a way of uniquely transforming the data into higher dimension. So if the data is in one dimension before, like this one now, this is one-dimensional data, only x-axis is taken care of. The same thing with this. However, since this one is linearly separable, it's easily done. But for this case, we cannot create a separating hyperplane here. So we have to transform this problem into this using the unique capability or unique attribute of support vector machine that we call the kernel trick. Yeah. It's so powerful that people have believed that this is one of the very unique attributes of support vector machine that always make it to work in areas where other popular algorithms often fail to perform. Like being able to work in the case of especially very few data samples. So once we push this data into higher dimension, for example, this one is just try to create a y-axis to make a second dimension for that. So we don't have value for y, generate it with this x is got y is got to x squared. It means every value you have on the x-axis here, just square them and use it to generate it. You can see that each of these points we shift to meet the corresponding value of the kernel. At that point in time, you can see here that it becomes possible for us to draw a separating hyperplane. Yeah, a separating hyperplane became very possible, which was not possible before. Now, so the secret behind nonlinear SVM or I'm using it to solve very hard problem for cases where the data set is not linearly separable. So this is the secret. We call it the kernel function. So this is an example pictorially. You have this kind of a situation. This is first class, this is another class. So you are looking for, you want to draw a line. We are not looking towards drawing a curved line. No, not a curve, but rather we are looking for a straight line. But there's no way we can do it here. So in that case, we have to use what we call kernel function. So with the appropriate kernel function, this data set can be transformed to make it look like something that becomes linearly separable. So this kernel is a function that maps the data to a higher dimension, where the data is now becoming separable. The help in projecting data to a higher dimensional space, where the point can be linearly separated. And this, of course, is one of the source of the huge computational complexity that support vector machines suffers from. Because everything with an advantage also has disadvantage. One of the disadvantages of support vector machine is that, especially during the training process, it takes a lot of time. So since if you have 1 million samples, each of those samples need to be transformed. And you can imagine that is the kind of computational complexity that's going to be involved. So you have to transform every sample to that particular, and depending on the kernel function you are using, because there are different types of kernel functions you are going to have. See, the general idea is that the original input space can always be mapped to some higher dimensional feature space where the training set is separable. So that is a very strong belief that a support vector machine has been based on. And I think I gave an example before that we can compare in real life to when you want to separate people. You get to your class, you want to know who is tall, who is not tall. This is very simple. We said this is a linearly separable case. Just ask everybody to stand up. Then you have a yardstick to quickly know. By looking at people, you know that, oh, okay, this person is tall, this one is not tall. That is a very easy problem to solve. However, when you have a kind of problem that you want to determine among your students you are looking at who can run a marathon race or not. It becomes very difficult to take that decision because sometimes looking at someone, you may underrate his or her capability. So, and somebody might decide to take you to court if you decide that you cannot participate in a marathon by just looking at his nature, his body build or physical look. That is a little bit hard problem to do. So what you have to do is to subject them to a particular test. Let them run from point A, from your class to the admin block of that school. By the time you get there and then run back, be able to separate them, who can run and who cannot run. So this can be comparable to the idea of having kernel function. So the kernel function, we will have pushed them after they run. Some of them might not make it back to the class because they'll be too tired that they will not be able to come back. Some might even need the support of ambulance to get themselves better. So by that time, when they return, you know clearly that, okay, this group of people, this one can participate in the marathon, this one doesn't have that stamina to do so. This is exactly or similar to what support vector machine does. So by the time you subject, look at these samples, you can see that these samples are clearly surrounded by another sample. Let's say this is class B, while this is class A. So there's no way you can draw. It's already on 2 dimensions, but yet it's very complicated that we cannot draw any separating hyperplane. Yet it's not possible to draw it. In that case, we need a kernel function that can help us push it to another dimension, another higher dimension. You see, this is X and Y axis. Now we've been able to push it to X, Y, and the Z axis. So at that point, you can see that we can easily draw an hyperplane between them. Yeah, we can draw a separating hyperplane now after this simple operation, which was not possible at this point. We are not looking for a circle. We can draw a circle around it. That support vector machine does not support that. Again, it's one of the limitations of support vector machine at the long run, because it means it can only separate 2 classes. If you have 3 classes, it cannot work on that. You have to have an indirect way of solving that problem. We'll talk about that one later on. Yeah. So by this kernel function, the system is able to push. The system is able to push the data, the training data, to a level whereby hopefully it become linearly separable, which is then that the support vector machine can do what it knows better how to do it. So this is another case, hypothetical case. You can see the data. You can see how they are spread. So with appropriate kernel, that data can become transformed to this format, so that clearly you can see the decision surface. You can easily separate it together. Anyway, you can see here, you can easily separate it. The same data that was not possible, look at how they are fully separated. So sometimes they depend on the kind of kernel function you are using. We have to use the appropriate kernel. Which kernel is okay, which one is not okay. We're going to talk about that. So the kernel trick, as the people popularly call the idea. So from our experience, this has been the very unique attribute of support vector machine. So the way the kernel trick works is that instead of explicitly computing the lifting transformation, you define a kernel function K such that this relationship holds. We then give a nonlinear decision boundary in the original feature space. Then your work can easily be carried out as intended. This separation can be done. So this is a sample of a simple kernel trick or kernel function that I mentioned before. So a simple mathematical transformation will be of this form, that the system can easily get result. Now, these are some of the kernels in a support vector machine. So we could have a linear kernel. Sorry, these are some of the nonlinear SVM type. We could have linear SVM, we have nonlinear SVM, and then we have the kernel function. So that can work the system or support the system. Now, these are type of kernel function that we can use. You can have linear kernel. So we have polynomial kernel. So polynomial kernel from experience always work, but some cases it doesn't work. And this is what we are going to establish. How do we know which one works? It depends on the data set. Of course, there's some feedback from historical research work that has been done that usually polynomial kernel is popular in image processing. So, however, based on the principle of let the data speak, we don't get too much attached to this kind of advice. See, once you have your data in the system, try to check. This is part of what we do in the in the procedure that we call parameter optimization. So in the parameter optimization or parameter search, you need to check for which parameter is going to work for you. And for support vector machine, the first parameter to check is the kernel function, because it's the most powerful hyperparameter. Yeah, we call it hyperparameter. Is the most powerful hyperparameter that had the highest effect on the possible outcome of your experiment. So you start from choosing the ideal kernel function. So after kernel function, then we are going to talk about the C, the regularization factor C. Is another very powerful hyperparameter of support vector machine. So once we have the first hyperparameter to really check out is the kernel function. So how do you check it out? So you cannot really be sure. The fact that you are working on image processing problem doesn't mean that you're going to guarantee always you are going to have polynomial as the best. No. So you start with the simple one, then check the polynomial, check Gaussian, check the radial basis function, and then once you put it, you record the outcome of the experiment. Check out the outcome of the experiment, which one is giving you the best result. So you compare them. You can make a plot in your Excel file if necessary to convince the reviewer that you have actually carried out this hyperparameter checking of their optimum one. So once you get the best one that works for your own data set, like I said, the principle of let the data speak must always be followed. Irrespective of whatever advices have been, these are just opinion. You can see that they say it's popular in image processing. It doesn't mean that it cannot work in other data sets. So we have seen some work that Gaussian is usually very common. It commonly works for every situation. But for some problem, we've noticed that polynomial will not even run. It will generate error for your data set. It will not even work in some cases. Depending on the kind of data set you are working on, it means it's not in line with the kind of data you're having. However, Gaussian kernel, no prior knowledge about the data is needed. We've noticed always work on almost any data set you use it for. Gaussian kernel will work. Work in the sense that it will run successfully, but doesn't guarantee that it's going to get the best result. So you have to do that of polynomial, get the result, check for linear kernel, check radial basis function, RBF, and then you have to come up and you can see the example of the formula for each of these kernel function. So once you do this hyperparameter optimization, then you come up with the best kernel function that is suitable for the problem you are addressing. So it is after that, you can see here, radial basis function, this is widely used kernel function, suitable if no prior knowledge about the data is known. This is just an advice. Like I said, nothing is dogmatic about machine learning. You just have to check out which one is going to work for your data set. The fact that polynomial worked for your problem you solved last year, even though in the same area, but now data set is different, it doesn't mean that the same polynomial will work in the another data set you have in the same, from the same area. So that is why when you build a model, and then in your report writing, it is expected that we want to see the hyperparameter optimization. How did you do that? Have you checked other hyperparameters? Let's say, for instance, you use two methods, you use neural network and support vector machine to solve a problem. You want to compare them together. So we noticed that in ANN, you carry out extensive hyperparameter optimization, but in SVM, no hyperparameter optimization. You just decide to use polynomial, and you got 93%. Meanwhile, ANN is getting maybe 95%, and then you concluded that ANN is better than support vector machine. So if the reviewer gets to know that you didn't carry out hyperparameter optimization for SVM, that is automatic rejection, because you are not being fair to this algorithm. Whatever you do to ANN, you have to do it to SVM. Often people say, okay, from my experience, I know that polynomial is always the best, it's always good, so I decide to go for polynomial. No, you don't do that. The principle of machine learning does not allow you to do that. You have to check out which one is going to push this algorithm to the best possible performance on this present data set. Don't assume. Don't make assumption that if polynomial has been working for all my problem in this medical area, then it's going to work for this case. No. So let us pay attention to that. So hyperparameter optimization is very, very important. So in support vector machine experiment, once we are able to identify the hyperparameter, then we can then move to other hyperparameter like C, like gamma, and others that we can have the opportunity of discussing finally, hopefully, or next time. Now, so when we have the nonlinear data, we say that support vector machine are trained by maximizing the margin, which is the amount of space between the decision boundary and the nearest example. You can see here. So if the problem isn't linearly separable, of course, we say there's no perfect decision boundary, and so there's no hard margin SVM solution. So, and this is why the kind of idea of soft margin SVM was introduced, which allows some point to be on the wrong side of the margin. You see, sometimes we could have a very, very complicated problem that no matter how you try to separate, you see, some of those data from another class will find themselves in the midst of majority opposite class. You can see it's supposed to be this side, but now it's here. So this is one of the reasons why I usually advocate that we do some pre-processing on the data set, because you know the kind of data set you are having. So the data set may be a little bit complicated with so many noisy data. That is noisy data we appear to belong to. By labeling, it might belong to A, but in reality, it might actually belong to B, but now it has been labeled as A. So you cannot unlabel it, because that was what came from the client, from where they got the data from. This could be the source. So during pre-processing and data cleaning, we might have the opportunity of kicking out this kind of data set. Otherwise, support vector machine, we use the idea of soft margin to still take care of such a data set. So this is where we're going to have an idea of slack variable. It's very rare in reality, but sometimes we do run into this kind of, let me say, minority problem with us to, you might have a case whereby opposite class, even after drawing the maximum possible margin, opposite class is falling in the midst of the wrong side. In that case, SVM still has the opportunity of taking care of it. So that's why we have this idea of soft margin SVM, which allows some point to be on the wrong side of the margin, as the case may be. And this also led to the idea of the slack variable I just mentioned. Is the slack variable that defines how much on the wrong side the ith training example can be. So if the slack variable is 0, the point was classified correctly and by enough of a margin. But if it is between 0 and 1, then the point was classified correctly, but by less of a margin than the SVM wanted. The SVM has to compromise the margin it's looking at to be able to take care of it appropriately. So, and if it is more than 1, then the point was classified incorrectly. So based on that, that is, if the margin that has to be given is over a particular threshold, then the slack variable will not be able to assess it. Then it's going to be wrongly classified. And it's okay. And that is why when you train a model, we are not looking for 100% training performance. You have to have some little compromise. After training, we got like 97% performance. That's okay. During your testing, you're able to get 96%. This is excellent, excellent work. It's better than having 100% training performance, and then when you want to test, it's giving you like 64% performance, which is a sign of what we usually refer to as, see, yeah, when you overtrain your system. You see, when you overtrain your system, you're going to run to this kind of problem whereby you have 100% training set, but the testing set is not able to meet up, or the generalization ability is too far away from the training system. So we need to avoid that. So that is why sometimes it's better during the training to have some little mistake from the training set rather than letting the testing set not reasonable compared to what you have gotten. Yeah, so mathematically, so we have some mathematicians among us. You can say the slack variable n can be added to allow misclassification of noisy examples, in which case, mathematically, we can formulate the support vector machine classifier as, so try to solve this minimize, we want to minimize. So it is the minimization, optimization problem. So for all the samples that have been provided, subject to this condition, where the C is what we call the regularization factor. After kernel function, the regularization factor is another very important hyperparameter that we have to look at to get better outcome from our support vector machine. Yes, finally, today we are going to just look at how does support vector machine compare to neural network, a very, very popular, another very popular machine learning algorithm. So we have the deterministic nature of the algorithm, where the neural network is not. It has a nice generalization properties. So here it generalized well. However, the mathematical foundation that is not as strong as we have in support vector machine. And also in the face of very few samples, when you have very few samples, neural network does not guarantee you work. It might not even work. Very poor performance if the data set is very few. So, but support vector machine is often hard to learn. So because it takes a lot of time. But once it's successfully trained, then getting your testing set become very faster because it's going to be based on the support vector. We have explained this before. So whereby support vector machine also had the idea of kernel function, the kernel trick, which make it to perform superiorly better compared to neural network and other aspects of it. So next time we are going to look into support vector machine, some of it, the unique stuff about it, how to decide some of the upper parameters to be trained, and also we are going to be able to mention to us how do we, because I told us we use support vector machine to solve only two-class problem. So when you have three classes problem, then support vector cannot solve that. We have to do it in an indirect way. See, we have to do it in an indirect way. So another few basic clarification that we have to make on support vector machine, and by the grace of God, in our next class, we're going to consider that. So we are going to be stopping here today to give room for people to ask some of their questions. There are a lot of popular websites, especially this website. We can check it out. We call it kernelmachines.org. So when you have kernel machine, they are referring to SVM, support vector machine. So we have several representative implementation, Lib SVM, SVM Lights, SVM Touch, and so many other representative implementation type from different people and also sources. So thank you very much for listening. So if there's any question, we're going to take a couple of questions, and then thank you.